Hello again. I'm following the same pattern as for number one, but one thing I probably forgot to mention last time was that I'll probably be scooting through these faster than I would do if it was a genuine lecture, precisely because you have the right or you have the ability to pause the video if and when you need it. So if I can mention the idea that quite a few figures are stated as accurately. You know, you have, if we talk, say, things like billiard balls or number of pens, you know, we can say 1, 2, 3. There's no doubt there, but in practice, a lot of numbers are in fact estimated. You know, you can have people come along and say, okay, we spent £2,000 on this, when in fact, you know, that was not the exact figure. It was just a nice round figure to give you a clue. Or you could just put a number down. You know, if you read a number off your calculator, which might have, say, 10 decimal places or something, and you could write it down with just, say, 1 or 2 decimal places, things like that. You know, it's an approximation. So these approximate numbers are happening all the time. I can just give you state how the procedure is for rounding figures off. You know, if I say, I don't know, 2. If I was to round that off to 2 decimal places, then I wouldn't necessarily just chop off any remaining places, any remaining digits. What I would do is that I would put a line in. You know, this is nominally the cutoff between that number I gave originally and the 2 decimal places. Now I need to examine this figure to the right of this dotted line, and the rule is that if this figure is 5 or above, then this number here is rounded up. But if it's 4 or less, then it's just discarded and it stays as it is. So yeah, this one here would just be 2.19 to 2 decimal places. But I mean, if it was, say, something like to 2 decimal places, that would be, again, if we could do it formally, you think in your mind's eye a line there. You look at that, and as I said, the rule is if it's 5 or above, you round this up. If it's 4 or less, then you just discard it. But the fact that you've got a 6 here, that means that this is going to be rounded up. So that is 2.44 to 2 decimal places. And the difference when you're talking about significant figures is 24.693. If I wanted that to 3 significant figures, then I'd look at the number as a whole. So I'd count in from the left. Again, this is my dotted line that I've got. You know, it's just really in my mind's eye. And again, you follow the rule. If you look at this figure here to the right of the dotted line, if it's 5 or above, you round that up. Otherwise, you just discard it. So okay, that's a 9. So we're going to round it up. So that becomes 24.7. This time it's to 3 significant figures. Okay. So there's that difference between quoting a figure to decimal places and quoting it to significant figures. Now, these what I call these inaccurate numbers. In reality, when you think into it more deeply, then they are quite widespread in reality. I mean, if I quote a height, you know, my height is 168 centimeters. You know, that's the way that people normally quote heights, but it's not. My height is not exactly is not going to be 168 centimeters exactly. That's the 168 is rounded up, and when you think about it, you know, the probability of people, if you go into it really accurately, the probability of 2 people having the same height is very, very, very low. So the question leading on from that is, if I quote a figure, you know, what range of figures does that figure actually represent? By that I mean, if I have 168, I mean, you'd normally quote heights like that. That's the way people normally quote heights. So I could say, if someone quotes a height as 168 centimeters, what is the range of heights that 168 does actually represent? So it seems logical to make a halfway point here between 168, 169 and 168, 167. So that line would represent 168.5, and that line would represent 167.5. Now, what range of values would be reported as 168 centimeters in height? Now, again, if I just quote it, it's going to be given by this expression. Right. So there's an important point here, which if you ignore it might lose you a mark or so. What I've got down at the bottom here is that it's saying that the height, this height, if I report it as 168, that height, real height, is going to be equal to or greater than 167.5. But at the other end, it's going to be less than 168.5. Okay, so you notice the difference in the inequalities here. The rule, I mean, the problem here is it's a bit, I don't know how you describe it really, but following on from what I've just said, that anything that falls on the line, because that's 5, if I'm quoting that to 3 significant figures, that would be rounded up to 169. So that anything that's actually on that line will be 169. So in order for it to be reported as 168, it's got to be less than that. And that's the only way you can report it, write it down in this manner. You know, typically what students, well, when I say obviously, typically what students try and do is try and think of a figure which is less than that and state it as the upper bound. But that can't be done. I mean, if you come along and say, okay, I'll say the upper bound is 168.4, then I can come along and say, well, what about 168.45? That's higher than your bound. And if someone comes along and says 168.45, well, I can say, okay, 168.455, that's higher. You just can't quote a figure that is, you can't actually quote the upper bound as an actual figure. The only way you can actually quote it is by saying this, it's less than 168.5. Right. Given that a lot of numbers are quoted to or rounded up, typically given to a certain number of significant figures, then there are rules for when you use these significant figures in arithmetic operations. Again, to just quote the rule is that if your input data is, for example, if your input data is given to 2 significant figures, then your answer must at most be given to 2 significant figures as well. I mean, to quote as an example from astronomy, you know, astronomy is one of my subjects, so I'll probably be bringing that in quite often. You might quote a figure as saying, oh, a certain galaxy is 245 megaparsecs away or something, and you know, for example, that is an approximation. You know, it's not exactly 245. But at the same time, if you realise that a megaparsec is a considerable distance, then there is a considerable distance between something that's 245 and something that's 246. You know, there's quite a lot of approximation here. So typically, you know, if students were given a calculation to do involving a figure like that, if the untutored student might come along with this figure, okay, I've done the operation using this, and I'll come along, use my calculator, and I've got a figure like this, and I'll present that as my answer. Then what I'm trying to say to you is that there's not enough information in this figure to produce an answer as accurate as that. If that's 3 significant figures, then that has got to be 3 significant figures as well. So you're going to have to just chop it off there. This is a bit more difficult. I've put this figure down at random, and having looked at this is a bit more difficult. What you have to realise is that will round up that figure, but obviously because that's a 9, that will then have the effect of rounding that up. So that'll be that to 3 significant figures. Okay, again, I'm going through these things fairly quickly, so that was a bit of an unfortunate choice on my part, but that's the what happens anyway when you're trying to round that up to 3 significant figures. As I say, we're going through this fairly quickly, so just take in what you can, and we would normally go into something in a bit more detail later on. Now, I mean, there are quite commonplace examples of things like this happening. You know, quite irritating at times. You know, by that I mean you get situations where people take data which has been rounded up to a certain number of figures or something, or whatever, and they do a bit of an arithmetic calculation on it, and they come up with a figure which is just too accurate. You know, you might have a newspaper article that says something like, you know, a car fell off a 60-foot cliff or something, and someone has helpfully said that that's 19.1 meters or something like that. But I mean, that's just nonsense. You know, when they talk about 60-foot cliff, that's not exactly 60 foot. That's been sort of approximated. So to come along and say, okay, that's 19.1 meters, that's just nonsense. That's the 19.1. You know, there's just not enough information in the original figures to give a figure as accurate as 19.1. You get this also with body temp. Body temperature is normally stated as 37 degrees, and you get in other countries, well, a country say like America, which quotes it using their system as something like 98.7 or something like that. I mean, again, it's just rubbish for the same reasons that I've just quoted in the previous example. 37 degrees is just an approximation for body temperature. To then go on and quote it as 98.7 in some other system, you know, it's just nonsense. There's just not enough accuracy in the original figure to quote it down to 3 significant figures. And apart from that, also, you know, the body temperature tends to vary depending on which part of the body you measure the temperature from as well. So that's an added problem. And also in Britain, you have an irritating, well, I find it irritating anyway, when they quote the speeds of cross-channel trains as 186 miles per hour, you know, which is, again, nonsense, because you don't normally quote figures as in that. It's normally sort of nice round figures like nearest 10 or nearest 5. And again, that's what they've done. They've taken the figure of 300 kilometres and converted it to 186, but you know for a fact that these trains do not go at exactly 300 kilometres per hour. So to produce an accurate conversion of 186 miles per hour, again, it's just nonsense. So I think I'll probably quote. I won't give a further example on that, but I just need to add a couple of riders to the effect that, you know, if you come along in an exam and they say, okay, 245 times 32 or something like that, then you don't have to bother about significant figures there. That's just an arithmetic problem which they've just stated as being accurate. Okay, so that's got 3 figures, that's got 2, but just, you know, do the multiplications normal and just quote it straight off. I should, in a normal situation, I'd also probably say that I don't really bother about explaining about long multiplication and long division. I'd probably ask students to research that themselves. But well, I'd say that here now as well. It might be in future. I might actually add a unit explaining that, but I'm not going to talk about it now anyway. I'll just finish off expanding a bit on those significant figures. If I think of a couple of extreme examples, something like this, 0, 0, 0, 0, 7314. If I need to quote that to two significant figures, I don't just go, okay, that's 0.0. That would be wouldn't tell me anything. In a situation like that, I ignore any leading zeros and I start from here. So that, because that's the 1, that is 0.00073 to two significant figures. Okay. And the other end, it might be something like this: 32,493. Okay, 32,493. If I'm going to quote that to two significant figures, well, again, I've got this here. That's a 4, so that's unaltered. Okay, but I need to add in the zeros to fill this number out. So that would be that to two significant figures. Okay, so that's taken me about a quarter of an hour or so to explain that particular topic, so I'll bring that to an end now, and thank you very much for listening if you're still with me, and hope to see you in the next one. Thanks very much. Cheers for now.